I would like to announce our next speaker. He will be presenting online, Kenneth Macleod. Sorry for pronouncing the surnames in advance. From Space Propulsion Synergy team. He will be talking about forecasting numbers of post-mission satellites and mitigation methods. Please, thank you.
Thank you, Jana. We're going to spend the next couple of minutes here looking at the potential of what is going to happen with the post-mission satellites. We're going to have potentially a lot of them as these large numbers of satellites get launched, and then as we pass one lifetime of them. So there's only 4 questions we're going to look at. One is background, and that is how many active internet satellites will actually get to orbit. Not the total number that have been thought about, but the number that'll get there. Second, how many post-mission internet satellites would be decaying downwards toward reentry at any time after we get to one lifetime? And third, what additional problems will these post-mission populations pose for the expected dark and quiet skies impacts that we care about? And last, and maybe most important, what's the best path forward for mitigation? So there's a lot of ways to count how many internet satellites there might be. Some of the counts run up above 400,000 today. But we've chosen to use the ComSpoc calculations. And here they add a fair amount of judgment of which ones will actually get launched. And so looking ahead to less than 10 years or so, the number that they estimate is around 100,000 satellites. And you're free to make your own estimates of that, but this seems like a reasonably relevant and conservative number to use here. We all know they're going up in volume. Here we see the 20 plus of them, each of the V1.5s and the V2s stacked for launch from SpaceX. So we know there will be a lot, and this seems like a reasonable estimate. There's only 2 things we really need to understand if we want to understand how many of these post-mission satellites will be in the decay spiral, decaying down at any one time. And that is, what's the intake rate to the decay spiral? And then we multiply that times the decay time once they enter the decay spiral, that decay time to reentry. And that gives us the number of each class. For this presentation, we've divided into 2 classes: expired satellites, which very often get a push to lower their altitude, and failed and damaged satellites, which very often do not get such a push, and therefore they tend to take much longer to spiral down. So this leads to fairly accurate calculations. Certainly be possible to have more classes than this. So the intake rate for expired satellites is simply the number on orbit divided by their lifetime on the average. Once we've achieved one lifetime. And the intake rate for failed plus damaged satellites is the number on orbit times the failure rate plus the damage rate. So the calculation is pretty simple. From what we've just said, the number of post-mission internet satellites at any time, is the intake rate after end of life, which is N over L, the number on orbit divided by lifetime, times the time it takes them to decay from end of life. Plus, those after failure or damage, again, the intake rate is the number on orbit times the failure plus a damage rate per year. Again, times the average, the TF, which is the average time to decay to reentry after failure in orbit, which is probably longer. So the important question is, what are we going to choose for these parameters? We've said already that we've chosen N to be 100,000 internet satellites, approximately. The lifetime we've chosen to be 5 years because that's what we're seeing. It's limited by the propellant for orbit keeping and station keeping. T sub L, the average time to decay for one that's end of life and has had a deorbit push, ranges from 4 weeks. We'll see that the Starlink satellites are proposing to do that for all their satellites to several years to deorbit. And we estimate that all the rest of the satellites besides the Starlinks will take about 10 months. on the average. This gives us an average of half a year for T sub L. The failure rate plus damage rate is very difficult to estimate. We've chosen 2% per year for this. You could imagine it's 1% failure rate plus 1% damage rate, but there's no easy way to know this. Clearly, it won't be 10 times higher and it won't be 10 times lower though. So it's the right order of magnitude. And then 3 years approximately for the decay after failure. This is for a low Earth orbit. This is 1 to 5 years at very low at 550 kilometers, but it can get much higher. Here's a typical chart of decay times versus starting altitude. The altitudes along the bottom only range over a few hundred kilometers, but the lifetime ranges from 0.001 years out to 1,000 years. So this is difficult, but we've chosen 3 years as we hope a reasonably conservative number. It'll be acceptable. So now that we know the parameters and we know how to calculate it, we can actually do the calculations. So here's the calculation for those after end of life: 100,000 satellites with a life of 5 years. So we have 20,000 expiring satellites each year that take a half a year to spiral down. So that says 10,000 satellites at any one time in the spiral from end of life. And then 100,000 satellites with a failure rate plus damage rate of 2% times 3 years of those that are in the spiral gives us a total of 6,000 after failure or damage. So we come to an answer of about 16,000 decaying post-mission internet satellites at any time after the full constellations are launched and we've had one lifetime. So the good news is this is only a fraction of the 100,000 active satellites because there is a certain amount of self-cleaning in low Earth orbit from the tenuous atmosphere. The bad news is that they're still quite important because they have additional observational problems that make them more troublesome. So what might those problems be? So here I picked 7 of them. We all know that they'll change orbital parameters continuously and not uniformly because of space weather as they decay. So it's much more difficult to plan ahead to do avoidance of them in observations. Second, they may lose attitude control, and they will as they get down low enough, and that can increase their brightness since reflective positioning is turning out to be a very important brightness control. Third, they may tumble, causing frequent bright flashes that are difficult to predict. And of course, they're also much more difficult to remove from images. Here's a picture of the Kobe satellite in 1992 after it lost control and began to tumble. Fourth, they'll cause a lot of reentry fireballs. The numbers we just showed lead to 60 reentry fireballs a day, half of those on the day side, half on the night side. They're very bright in the optical and IR, and they're reflected in RF, which can also be a problem. Fifth, they could transmit radio signals if the failure leaves them. If the failed ones fail in a way that leaves the radios on, they could transmit more powerful signals than we would like at our very sensitive radio systems. Sixth, their decreasing altitude leads to increasing brightness due to 1/r squared. If they decline from 600 kilometers down to only 150, they're 4 times closer at their closest point and therefore 16 times brighter. But of course, that also leads them to be mostly in shadow, which we like. And they could also potentially collide with each other, yielding what I call rapid changes in the debris catalog. So we all know what the mitigations have been so far, and there's a lot of excellent choices here. So there's a lot of dimming efforts. I've listed dark coatings, visors, dielectric mirrors, angling away from the sun. This does not get around occulting, however. The satellites are growing much larger, much more numerous, and our observations are growing much more dynamic. So we all know how big these look because we've seen this picture so many times. But that says it could be a new problem in addition to some of the old ones. Second, we know that the FCC has improved their deorbiting time limit. Next, there are best practices from a variety of very thoughtful organizations. There are bilateral agreements. We've seen NSF and SpaceX Starlink now. and OneWeb and Kuiper are said to be coming soon. There's the possibility of reduced population size. AST has pointed out that they only need 90 satellites, and so people are beginning to consider how many they have. But still, that's limited by the 1 over r squared again, because these have to have proximity to small mobile terminals on the ground where they don't work. So these are probably necessary and welcome, but not sufficient. So let's look at some other mitigations for post-mission satellites. There's the rapid deorbiting that could spread to others. Starlink proposes to deorbit in 4 weeks, which requires them to retain, more argon than they probably want to. It's a big step forward. We could choose redundant systems and armor, which could reduce the failure and the damage rates on orbit. It adds cost and mass, but it may be appropriate. Some discussions have been of a watchdog timer and a backup controller to provide a deorbit burn upon failure or damage, or a similar watchdog timer deploying a drag tether or a drag balloon or a drag sail. And last, and quite interesting, is the idea of a service cleanup satellite in each ring. There's a big opportunity here because these satellites are deployed in rings. Here's a typical picture of the that we've all seen from Wikimedia of the first phase of the Starlink satellites. And there's 22 satellites in each of these rings, and the rings are very close together. So you could have a cleanup satellite that could drift around the ring to any troubled satellite with very low delta V required for an incremental change in altitude. Then it could drift around and then restore its altitude to the full altitude. These could deorbit or refuel or service troubled units. If they could refuel twice, and that would triple the length of time of the lifetime of these satellites, that would reduce the intake rate of the expired satellites by a factor of 3, which is a very big deal. A recent U.S. government request for proposals got 23 companies who were interested in developing satellites like this. So one more thing, we could conceivably accelerate a path forward here by having a joint development and testing organization. All of these mitigation methods that are described require development, testing, systems engineering, and trade studies. And it could be very helpful to have some kind of a joint organization. I have experience on the terrestrial communications with Cable Labs, the Wi-Fi Alliance, IEEE 802. All of these enabled a lot of smaller companies to punch above their weight. And this could easily be operated as an adjunct to an existing organization. I'm speaking from the US, and here are a few US examples that come to mind where you might cite such a joint development organization. So now we've got the conclusions to all these questions. A reasonable estimate for the number of satellites that actually get launched in 10 years is perhaps 100,000. The total number coming down to re-entry at any one time after a lifetime is about 16,000. We've noted what the additional problems are for astronomy observations and several mitigation methods that could be effective, and the possibility of a systems engineering joint lab that might be helpful as well. I want to mention one thing before I go, and that is I think we need to talk to people about the scope of the capital investment that we have coming into service at this time. Every time we talk to people about this, and every time I look at comments online, they all say, "Why don't you just put your telescope in space? Then you don't have any problem." Ignoring the deprecating this very large investment in time, energy, and talent that's going on. Thank you very much. If there's time for questions, I'm happy to take questions.
Thank you very much, Kenneth, for your interesting and insightful presentation. Do we have any questions from the audience? Yes, here.
Probably more of a remark. It's Richard Green. I think you've you've highlighted one potential trade study that we ought to make, because we don't have any love from a reflected sunlight point of view of drag sails. And so we would want to see a trade-off between deploying those and the reduction of debris producing collisions and things like that. Is there any intuition on how that trade would go?
I think you'd have to start with very black drag balloons or drag sails to make any progress.
Thank you very much. I think we can continue this discussion online. Thank you, Kenneth, again for your presentation.